Okay, we try and have a look at the idea behind the definition of Irms, okay, which is in your notes. Right, if we were to have a look at an alternating current source, okay, attached to a resistor, okay, what kind of graph will this alternating current source produce? Right, so I'll try and draw the graph for you. Okay, the x-axis in this graph is time. Alright, time in seconds. Okay, the y-axis actually represents a variety of things. It can represent voltage, it can represent current, and it can represent power. Alright, so basically I'm not going to name the y-axis because of this. Okay, so if I have an AC source, okay, the first thing I know is my AC source must set up a potential difference across the resistor. Okay, so this potential difference will start from 0, increase to some maximum value which I call V0. Right, so V0 represents this point over here. Okay, and it will go down to 0, okay, back in the other direction. Right, so now this will be high potential and low potential, when initially this was high and this is low. Alright, so in any case, this is a sinusoidal AC source, okay, hence I will produce a sinusoidal potential difference that I apply across the resistor. Right, so with this potential difference, I will exert a current across the resistor. Right, so the current value can be given by V0 over R, where R is the resistance. Okay, so the current value will be 0 when PD is 0. I'll increase to a maximum value I0. Right, so this point here, right, directly below the V0 value will be I0. Right, I0 can be given by V0 over R. Alright, so any point the current here can be found by taking the potential difference divided by R. Right, so if the PD is a sine graph, the current I should expect to be a sine graph as well. Okay, so knowing this now that we have the blue and the red lines, okay, how are we going to find power delivered to the load? Alright, so the power graph you should know to be equal to the general equation for power equals to V times I. Right, so if I want power at this position, I take V times I, which gives me 0 quite clearly. Right, if I want power at this position, I actually need to take V times I. Right, so V times I value will give me this power. Right, why is a lower value is because if one of them is a fraction, right, then the multiplication of the two can give me a lower value. Right, so as I go up, this graph will start to shift upwards. Alright, and at this point over here, the maximum power can be given by V0 times I0. Alright, where this is V0 and this I0, so I multiply these two values to get this. Alright, what you need to observe about the power graph is that it is neither a sine or cosine graph. Alright, or if it is if you want to think of it like a negative cosine graph, it's a negative cosine graph that is shifted upwards. Alright, so this is actually a special graph. Okay, take note of this region in the graph simply because this is not the shape of this area of the graph is not downwards like a normal sine graph. Right, it actually approaches 0 with a dropping gradient. Alright, and if I follow through, this part should be going up, right, as per this part over here. Right, so the curvature here, when you find the power graph, please pay attention, is not the same as a sine graph coming down to 0. Okay, this one the gradient is increasing coming in. For power, the gradient is actually dropping. Alright, so now I have the power graph. Alright, it should look something like that. Okay, why is this positive power? It's simply because negative V0 times negative I0 should give me positive power also. Right, so the power is always positive, it can never be negative. Alright, and it's some kind of cosine graph that is actually shifted upwards. Alright, okay, so we now just want to have a look at the power graph. Okay, if I just have a look at this black graph and I shift it over here. Alright, if I look at this black graph over here, this is my maximum power value. Okay, this is P max. Okay, if I want the average power, okay, I can look at this part, one period. Okay, I always look at one period, and then I can cut this part into half, and this shaded area can be dumped inside here. Right, because it's symmetrical about this point. Right, so this shaded area can be dumped inside here. Conversely, this shaded area can be dumped inside here. Right, so if I want to take average power, basically I want to make this curve look flat. Right, to make this curve look flat, I take this area dump here and I take this area and dump here, and that gives me average power. And since this thing is symmetrical, my average power is clearly half the maximum value, or I call this P0. right? Sometimes it's called P max, sometimes it's called P naught. Okay, basically it means the same thing, right? So from the graph, I know my average power is actually half P naught or P max, so I get this equation over here, right? I also know P naught to be V naught times I naught, right? Since average power is half V naught I naught, right? And we also know that for this V naught, for this potential difference graph over here with a maximum value V naught, the VRMS value will be given by V naught over root 2. Correspondingly, for this sine graph over here that represents current, again sinusoidal, hence if I look at the RMS value is I naught over root 2. Okay, realize that when I look at RMS values, I'm looking at the AC current as if it were a DC current. Alright, so the IRMS value is actually the DC version of the AC current. Okay, and how do we obtain the DC version of the AC current? We want to make sure that the AC version and the equivalent DC version actually deliver the same power. So if I look at this actual circuit, the power delivered is this thing, right? But I want to look at average power. So average power is actually this line over here, P average, which is given by this value, half V naught I naught. Okay, this is the average power delivered by this AC source. And this average power, how do I deliver it if I can somehow make all this AC into DC? Okay, the other way I can deliver it is if I have a perfect transformer and convert this into pure DC, I'll convert it into a DC with current equals to this, right? Because realize that this is a DC because it's a straight line and it doesn't pass through the other, it doesn't become negative at any point of time. And also this is also DC, right? So this is like a constant potential difference producing a constant current, right? And what's the power delivered by this DC PD and this DC current, right? Do you realize when I multiply these two, I exactly get half V naught I naught, right? And that's why it leads to what you are trying, what the definition of IRMS is. Okay, the root mean square value of an alternating current is defined as the equivalent value of steady direct current that will produce the heat at the same rate as the alternating current in a given resistance. So in a given resistance, the IRMS value, okay, is actually the equivalent value of a DC steady state current. So this is the DC steady state current that will produce the same heat as the alternating current, right, which is the black power line, right, given in a given resistance. Okay, producing heat at the same rate means power, right? So the DC version must produce the same power as the AC version. Okay, so that's what this definition is trying to talk about. Alright, so in this case, quite clearly, the IRMS value here multiplied by the VRMS value here gives me the same power as the AC version, right? Because this multiplied by this gives you half V naught I naught.